Oh, okay, that's it.
It's
That's what we
okay.
want. Yeah, yes.
Okay. Okay, then I ready.
Yep, you can start.
Okay, yes. All right, so thanks everyone. So let's start with the next talk. So the next talk is by Alexander Bobylev, who will talk on solutions of Vlasov-Poisson-Landau equations for slowly varying in space initial data. Thanks a lot.
Thank you. First of all, I would like to thank organizers for the kind invitation to give this talk. Sorry for I could not come. The title of the talk is On Solutions of Vlasov-Poisson-Landau Equations for Slowly Varying in Space Initial Data. This is a joint work with Irina Potapenko. Let me begin with the motivation, what I would like to discuss. So, there is a qualitative difference between the Boltzmann equation and the Vlasov-Poisson-Landau equation, which I want to stress. Our problem, normally kinetic equation plus boundary and initial conditions, can include different length scales. For a Boltzmann equation, we have first mean free path L, and second macroscopic length L, which is often much greater than L. Then the solution with the typical length L capital, macroscopic length, correspond to what I call long wave asymptotics. But if you consider the same problem with the plasma case, Vlasov-Landau equation or Vlasov-Bolescu-Lenard, whatever, it does not matter, but always you have three at least scales. There is the smallest scales, Debye radius, then mean free path, and then maybe macroscopic length. The question is, can we construct solutions with typical length, for example, of order of mean free path? This is more or less what I call long wave asymptotics in this case. So, and as a background, there is a lot of many numerical papers in last decade which study certain limit which I want to discuss. My notations now, I want to pass to equations. My notations are a standard F distribution function. X is a position. Everything is in three-dimensional case. V is the velocity, and T is the time. Mass is the mass of particles. I will consider normally one sort of particles for plasma electrons. General kinetic equation, Boltzmann and the Vlasov type, looks like that. F sub t plus V d of dx plus F capital, it is a force divided by M, d of dv equals collision term C of F. Now, we choose the initial condition. We consider, for simplicity, we don't consider boundary value problems. We consider the problem in the whole space with the equilibrium at infinity or periodic problems. In any case, we can choose the initial data in such a way that this is some constant proportional to function of variables x tilde v tilde, which are x divided by L0 and v tilde divided by thermal velocity. So T0 is the initial temperature, divided by m. Of course, Boltzmann constant is 1. And the rho 0 is a density. So, and as I say, that we use a periodic problem, periodic boundary conditions, or the whole space with the standard Maxwellian at infinity. So by standard transformations, we can pass to dimensionless problem, dimensionless variable, and finally we will have the equation which is shown at the bottom of this slide, ft plus vfx plus constant a times fourth term, and equals another constant b multiplied by the collision integral. And we will have the initial data which does not contain any parameters. All parameters are of order 1. Thus, we always have 2 parameters. First, what I denote to A, it is something that characterizes the force, and I always mean self-consistent force if it exists. And second, the parameter B, which characterize importance of the order of collisions. So these parameters are functions of L0, which I consider as the main control parameter, and also density rho 0 at time 0, and T capital 0, which also is considered as a constant. And we can always choose other parameters are microscopic, like mass or charge of particles. They are less important. So in fact, the most important parameter for me is L0, typical length of initial condition. And I will see what happens if I change it, and in particular make it large. And we can always choose such notation that A is and B are non-negative. The simplest example is the Boltzmann equation. When the force term is 0, I always consider only self-consistent force. And therefore, we have the only parameter B, and it is simply 1 over Knudsen number, where Knudsen number is the ratio between L, mean free path, and L0. In particular, this is a formula for mean free path for hard spheres. So the long wave asymptotics for the Boltzmann equation means simply the hydrodynamic limit when Knudsen tends to 0. This is well studied, and at the same time, the plasma case, Vlasov-Landau equation, is much more complicated because A is not 0, and moreover, A is much greater than B in that case. In fact, let me pass to Vlasov-Poisson, Vlasov-Poisson-Landau equation. So we consider a simplified physical model. This is a standard classical model, gas of electrons with the neutralizing background of infinitely heavy protons, distributed in space with a constant density rho 0. Then the dimensionless equation reads ft plus vfx minus a phi x dot FV equals B collision term. Collision term in that case is the classical Landau equation for EE collisions and the linear term for collisions with the ions, and plus, of course, Poisson equation, where rho is always the density integral dVf of V. Now I will show you Landau equation, Landau integral in standard notations, and linear collision term, which is a certain form of this type of integral when infinitely heavy ions have a distribution delta of V. But I will not use these formulas in this talk because I will consider mostly some model type of collisions because most importantly, I want to understand clearly what is the interplay between different scales. Now, this interplay depends on two parameters, and then you can easily calculate that for this particular equation, A is equal to L0 divided by RD, where RD is the Debye radius, and B is, of course, always 1 over Knudsen. So here I gave a standard formula for Debye radius and mean free path. But what is important that a mathematician can say that, okay, I have equation with two parameters. I can consider a property of this equation for different values of parameters. And that's it. But the problem is that the equation is valid, itself equation is valid only under certain condition. And this condition, of course, gives the relation between parameters. What is this condition? The condition is that so-called plasma parameter, the number of particles in the Debye sphere, must be much greater than 1. I prefer to use delta, which is inverse quantity, and which is much less than 1. Then these are standard relations, in particular between L and RD. L is the mean free path is always much greater RD, and therefore A, even a square root of A, is much greater than B for all practically interesting parameters L0. So L0 from the very beginning is not supposed to be small, is just arbitrary, but at least it must be greater than Debye radius. Thus, the collision terms are formally always much smaller than the Vlasov force term. So the smallest length scale for Vlasov-Poisson-Landau equation is obviously the Debye radius. Therefore, the long wave asymptotics for this equation can be defined as a formal limit when A tends to infinity and B, which is 1 over Knudsen, is bounded. Introducing a small parameter, epsilon equals A to power minus 1/2, which is simply Debye radius divided by L0, and it must be very small, we study below this limit, actually limit epsilon tends to 0 for relatively simple problem. Precisely the same problem was studied in many numerical works. Our goal is to clarify some mathematical aspects of this problem. So it will be 1D in space problem for Vlasov-Poisson-Landau equation. We assume that X was one-dimensional, V is still three-dimensional, and we introduce the dimensionless electric field E equals A times phi X, where phi is the potential. And then the result reads. Now I write F epsilon just to stress the dependence on epsilon. So F epsilon T plus V F epsilon X minus the fourth term equals 1 over Knudsen C of F epsilon. And here the electric field, the dimensionless electric field E satisfy the Poisson equation in the form E dx equals 1 over epsilon square 1 minus rho epsilon. So therefore, as you can see, there are two parameters, and I want to consider behavior of the solution for small epsilon. Moreover, I choose typical initial conditions in the form of local Maxwellian with a temperature T0 of X and with a density 1 and bulk velocity 0. This is assuming that T0 tends for large X to 1. The matter is that all these numerical papers I mentioned, they were done for this specific, very specific initial conditions, which look like typical, right? I denote below row for brevity, to avoid integrals, I write integrals like integral of dv f psi equals f psi like a scalar product in angular brackets. So then rho is f1 and j is the current is fvx, so the first moment. So now, first of all, let me tell you that there exists a formal limit of the Vlasov-Poisson-Landau equation at epsilon equals 0. So, under some assumption on good behavior, of course, everything is formal. In my paper, I don't do rigorous proofs, but they can make rigorous in some special cases, in particular in linearized cases. So we can formally prove the following: that limiting functions f0 before I wrote f epsilon, so now epsilon is at the formal limit epsilon equals 0. So limiting function f0 and e0 satisfy the following equations. So first is a standard Vlasov-Landau equation with E0, but E0 is not given by Poisson equation, but now it is given in explicit form. E0 equals 1 over Knudsen, the scalar product of collision integral with a Vx, and minus x derivative of F0 Vx of the second, roughly speaking, of pressure. And this equation implies equation implies that rho 0 at all time t will be 1 and g0 will be 0. So only the only relevant hydrodynamic quantity will be temperature, and there are many numerical works when people solve this equation. So let me stress that it's this equation's formal limit is almost obvious, because if you look at equation for electric field, here you multiply it by epsilon square, and you have 0 in the limit on the left hand side, and then you have rho 0 equals 1. To keep this relation, you need to satisfy equation G0, J0 current, because d rho dt equals minus dg dx, dj dx. Okay, so continuity equation, and the formula for E0 follows then from equation that the first moment of f remains constant. So it's very easy to get, and this is a few references to numerical papers and also to mathematical works. There is an enormous amount of mathematical works on Vlasov-Poisson-Planck equations, but to my knowledge, they don't consider this specific details. What I want to consider here, the difference between scales. So there are at least two interesting mathematical questions related to this limit. So the limit, again, I want to stress that this limiting equation, you can see here, equation 1 shows that you can construct a nice, formally, you can construct a nice solution when you don't have the Debye radius, it disappeared, and you have a typical time is the collision time, and now the fourth term is in this limiting equation is of the same order for Knudsen of order 1 as the collision. And this is very nice and in a sense unusual. So, but is it possible to prove something rigorously? So I repeat that there are two questions which I want to clarify. First is justification of this equation, and second is well-posedness of this equation. I will not speak in this about well-posedness. It is another topic, but I just tell you that it was shown in our previous paper in 2019, then that the answers to both questions are at least partly negative. So this does not mean that equations are too bad. They actually, at least at the linearized level, you can prove that equation, the limit for the distribution function really seems to be satisfying the limiting equation. But it is not correct for electric field. The formula which I showed before, that E0 equals some nice expression through first and second moment of collision integral and distribution function, is in a sense incomplete. Let me explain in which sense. These are related mathematical works on Vlasov type equation. And I must say that in well-posedness, collisions change almost nothing. Therefore, I don't want to discuss this. It is no more or less the same. Roughly speaking, what if the initial data is stable for Vlasov equation, then you have a well-posedness. Otherwise, you have ill-posedness. This is the situation. But let me concentrate from now on behavior of electric field for small epsilon. So I can prove the following again formally, but it's supported by numerics and looks and also I can prove it for linearized equation. Under some assumptions on behavior of f epsilon and e, epsilon natural assumptions, of course, the following asymptotic formula is valid for short times. That e epsilon is this formal limit E0, which is actually not limit, because the next term is E0 at time equals 0 times cosine t, and plus the error term of order of epsilon t. So thus, electric field E of x and the t rapidly oscillates with the plasma frequency, which is in our units 1 over epsilon, near its average E0. So somehow the previous formula for formal limit was only this is the formula which we obtain in the formal limit. It gives us only the average limit in the average time average of electric field. But in fact, there is also the rapidly oscillating term, and therefore we don't have a pointwise limit at all. And what is important that this term has amplitude O of 1. So it is a term we generally speaking we cannot neglect. So, for example, this amplitude for this Maxwellian initial conditions is simply the x derivative of t0 with a minus sign. T0, I mean the initial data. And the extra term in kinetic equation lead only at the same time. This term, if you try to solve the previous equation with a more exact rapidly oscillating electric field, so it gives only a small perturbation of the limiting function because of fast oscillations. It is a well-known effect in mechanics. But it is important if we are interested in exact data for electric field. So, okay, I don't want to speak about idea of proof, but important thing that the equation for electric field can be written as a second order in time equation with the left hand side epsilon square I second derivative of E plus E equals some source term, and we have a very nice initial condition, zero E and zero time derivative of E. Therefore, we can use Laplace transform and reduce this to integral equation and then more or less standard transformations gives the result. Okay, so I ignore for brevity well-posedness, and so I formulate the main result which was for electric field obtained in our paper 3 years ago, that we studied a class of such solutions of Landau-Vlasov-Poisson equation, for which a typical length is much bigger than the Debye radius, and taking the formal limit when epsilon, say, Debye radius tends to 0 and the Knudsen remain bounded, we obtain the kinetic equation, which was studied numerically in several publications. And what we prove that the limiting equation yields probably correct results for distribution function, but not for electric field. The extra term proportional to cosine T over epsilon was given in proposition I discussed before. And well-posed, this equation is well-posed for initial condition close to local Maxwellian. However, there are classes for which the equation is ill-posed. Okay, now let me discuss a very recent result. I need to discuss 3 points. First, key role of collisions in damping of plasma oscillations. Second, extension of a class of initial condition. And the third, numerical examples. Let me begin with the damping of plasma oscillation. The main remark is the following: there is no collisionless damping for long waves. The Landau damping of electrical field for epsilon near 0 is exponentially small, because the well-known formulas in our variables show the decay of electric field is given by exponential minus gamma of epsilon t, and gamma of epsilon is some constant and 1 over epsilon to the 4 exponential of minus c1 over epsilon square. So exponentially small. And this also, of course, constants are C0 and C1 are positive. This is this also can be seen in numerical examples. I will show you in a moment. The model BGK-type collision terms, because these things do not depend on collision term. Of course, I can use a linear BGK like in many papers at this conference, but it is not very important because this is a play between parameters, not between a specific form of collision integrals are not important. So the model type collision BGK type collision term give in this case the approximate formula, which is very close to the formula before, that E of x equals px, p is the pressure, and plus term rapidly oscillating term, which I showed you before, and times some exponential minus lambda t, where lambda is some constant beta over Knudsen. This is a more or less model kind of formula, which shows qualitatively how the collisions influence these oscillations, which I was again. P is exactly the second moment Vx square with Vx square of the solution. Now let me speak about initial conditions a bit more. Note that we considered the standard Maxwell initial data that F is equal to local Maxwellian with a given temperature T0 of x and with a constant constant density and with a constant zero flux. And you can easily understand that these conditions give very nice initial data for electric field, because electric field is zero, and even time derivative of electric field is zero at the initial moment. The question is, what happens if we slightly extend these initial data to F0 equals F capital 0 plus epsilon F capital 1, where density F capital 0 have a density 1, and the current given G0 of x, and the F1 also have a density minus E0, E small 0 of x, and 0 current. Then we obtain the following Cauchy problem. Here again is a standard our equation, and the initial data is like that. On the other hand, also we have equation for electric field in the form epsilon square dE dt equals J, which is the first moment of F, and the initial electric field is E0 divided by epsilon. This is ET must be not epsilon. Yes, by epsilon. Okay. So this initial data lead to much larger values of electrical field, because at time 0 we have initial electric field of order of 1 over epsilon, and then the time derivative 1 over epsilon square. So it is shown that there is a at least formal solution for short times in the form of asymptotic, hopefully asymptotic series in epsilon as a functions of a fast time. And by the way, the E also has the factor 1 over epsilon in front of this sum. This is very well supported by numerical and numerical results, and I show you only E0 and F0. They are given in elementary formulas. These are leading terms. Of course, this is only for small short time. Now I come to numerical results. We take a simplified one-dimensional in both velocity and x. I simplify further because, again, it does not matter dimension, etc., because this is related to behavior of plasma oscillations, which are more or less the same qualitatively in the one-dimensional case and in a higher dimensional case, at least. And so we have numerically we have this Vlasov-Poisson BGK equation. I will show you. This is a BGK collision term, and plus we use the following equation for E for electric field. It is convenient, and we compared a result with the formal limit when epsilon equals 0. In that case, we simply, like, if you look at this equation, you can easily see. And when epsilon equals 0, then you will have this formula for electric field. Now, initial conditions are, of course, F0 and E0 and the time derivative, which is given by J0. And again, angular brackets, of course, in that case, denote the integral over R instead of integral over R3 before. So we use the simplest BGK moment model for the collision term. This is this Maxwellian have this form with zero, contrary to standard BGK, with a zero bulk velocity. It is clear why, and of course with a rho, which is a rho for density for this function, the total mass, and the bulk velocity is zero simply because collisions of the standard the Landau type of the collision integral gives in that case don't give any momentum conservation because of collisions with ions. Collisions with ions conserve only energy and mass, of course, because ions are infinitely heavy and fixed. So there is no exchange of energy, but there is a big influence so you can easily understand that in that case we need to have this type of collision integral, and we solve these equations in the interval 0 to pi with a periodic boundary condition, with and use different velocity or different values of epsilon and Knudsen. So there are two classes of initial conditions that we consider, including the collisionless case when we just put Knudsen equals infinity. So first class is this local Maxwell initial data when T0 of x initial temperature is given by formula 1 minus a cosine x, and E equals time derivative of A at time equals 0 equals 0. And the second is more complicated. This is from the second group of initial data when so it is the same Maxwellian, not the same because temperature is a bit different, but multiplied by A of x and v, where A is 1 plus v cosine x divided by T0 plus v square. So upper index is not power, so is not in temperature in square. Yes, is just a second version of temperature. And let me show you. The first two figures are for the case Knudsen equals infinity. So and for purely Maxwellian initial condition. You can see the red line. Red line is what we have from our limiting equation at epsilon equals 0. But you can see that in fact, for any finite epsilon starting from 1 and to 0.004, we have a completely different picture because we have oscillations. By the way, here is this curve is finished here because it is just a constant after that for a larger time. Here is the time, and it is electric field. In all my pictures, it will be here the electric field and the time. And you can see here that the damping, for example, when epsilon equals 1, correspond to L equals Debye radius, very short waves, and you have a very nice Landau damping. They dump very, very quickly. But when you take smaller and smaller value of epsilon, you have slower and slower the damping of the oscillations. And we were not, you can understand that it needs a very, very small time step to describe these oscillations with sufficient accuracy. Therefore, we were not able to show exactly that there is no damping when epsilon equals 0. But it looks these are in logarithmic in logarithmic scales curves for damping of oscillations for smaller and smaller epsilon. And you see, so we believe that this means it corresponds that there is no, to the fact that there is no damping in the limit. Now, all other figures correspond to initial data of the second type, when we have initial current. Then we have much more interesting pictures, and the gray lines corresponds to Knudsen infinity. So it's a pure Vlasov equation. But when we include collisions, then it is very clear how the oscillations disappear, almost disappear after, say, certain collision times. But still, they are important in some time interval. And this is the case electric field in the point x equals pi. And this is electric field in the point x equals pi over 2. Epsilon in both cases is 0, 0, 1. So this is 1, and the Knudsen is 1 and infinity. Infinity means a Vlasov equation. And this is pictures for dpdx minus dpdx, which are average values of these quantities. And finally, I will show you transition to hydrodynamics. In some sense, if we try to consider also relatively small values of Knudsen, and at least it is seen that this is the first stage is roughly, this is initial stage, and this looks like hydrodynamic stage when you practically don't have a solution, the oscillations. And you can see here then the order of typical time is now 1 over Knudsen. So the smaller Knudsen, the slower is relaxation. But in that case, of course, this is hydrodynamic is in a sense very simple, because you have in this case rho equals 1. No, is not that, but at the beginning, at the end, it will be simple. I meant that for first Maxwellian initial, purely Maxwellian initial data, you have a very simple hydrodynamics, because only non-trivial quantity is a temperature. So you have just a nonlinear equation for temperature. Now I come to conclusions. So we study a time evolution of initial conditions for Vlasov-Poisson-Landau equation, having the typical length L, and then we use parameters Rz divided by L, which is tends to 0, and Knudsen, which is normally of order of 1. The initial data for dimensionless equations belong to one of two classes. First, rho 0 equals 1, j 0 equals 0, or rho 0 is 1 plus O of epsilon, and j 0 is O of 1. In the case A, there exists a known formal limit for Vlasov-Poisson-Landau equation at epsilon equals 0. The corresponding limit equations were used in several numerical papers. However, it was shown that the pointwise limit for electrical field cannot exist, because the field includes some rapidly oscillation terms. We show that these oscillations can exist for a very long time without damping if one neglects the collisions. Despite the smallness of collision term, only collisions can reduce the amplitude of oscillations. The first conclusion is that there is a certain stage of evolution of the system with a duration of order of several collision time, when the oscillating term in electrical field are not small and cannot be neglected. At the same time, they do not influence the lower moments of distribution function. This conclusion is confirmed by numerical solutions of simplified BGK-type model of the equation. The difficulty in the case B is that similar fast oscillations of electric field have a very large amplitude of order 1 over a epsilon at the first stage of evolution. The solution of our equation in the form of power series in epsilon is constructed in this form. Hopefully the series are asymptotic for small epsilon, so we did not try to prove this. We also studied numerically a relaxation of typical initial condition in the case B. The results show that the strong oscillations are also damped mostly by collisions. It takes several collisional time to reduce significantly the order of strong oscillation. Then the evolution became more or less similar to the evolution in the case A. For large values of time, the oscillations are damped, and the evolution becomes similar to hydrodynamic behavior. The transition to hydrodynamics, of course, especially in the case B, needs further investigation. Thank you.
Nice talk. Are there any questions? Yes. One.
Comment and question. Thanks, Sasha, for this super talk. And just general remark is that the way you introduce the oscillation at something quite, it has a counterpart at the level of math in speaking of well-posed or ill-posed initial problem. But then what you show is how it is general, how it goes on all the class of plasma physics. So then I have a question, is because there are two companion problems. First, you talk about hydrodynamic limit. Then there is the Benet equation, studied by Sakharov. Can you comment on the relation between this instability and yours? That's, let's say, an example. The other thing which is in the literature of plasma is the quasi-neutral limit, which appears in your talk when you have rho minus 1 over epsilon or the epsilon square. Can you also comment in relation between the quasi-neutral limit and what you do? Thanks.
Thank you. Sorry, I lost the picture. Oh, did you hear me? Do you hear me? No. Something. Is something wrong? Okay.
We can hear you. Can you still hear us?
You can hear.
Yes.
Okay, but I can try. Unfortunately, I lost the. So let me. No, it's not lunch meeting. Sorry, I lost the connection. Okay. No. Yeah. Oh, sorry. Do you hear me, Claude? I need to come again. Not very much.
Okay, maybe you guys should correspond via email if it's not working.
Yes, thank you. I'm sorry
Okay.
because yes, I lost.
Okay, yeah.
Claude, but anyway, it is very nice to thank you very much and for your kind words, and I am very happy to hear you.
Okay, great. Yeah. Thanks a lot. Thanks a lot for the great talk. Let's thank the speaker again.
Thank you very much. Oh.
A break, and I think as a